Welcome back to Complex Analysis. So we're getting into a new chapter, Chapter 3, and just to give you a quick overview, Chapter 3 is about sort of extending the calculus functions we dealt with into a complex setting. Okay, and our first sort of extension, if you will, is Mobius transformations. Now you might be like, wait, I've never heard of a Mobius transformation. What the heck is that? Well, think rational functions back from pre-calculus. And not like every type of rational function you would deal with in pre-calculus, but sort of like the simple ones. And we'll make that a little bit more precise later. Now you might be thinking, oh, you spelled pre-calculus wrong. That was actually for dramatic effect. Moving on. What is a Mobius transformation? So definition, a linear fractional transformation. Kind of a mouthful, but just think about fraction with linear on top and bottom. So a linear fractional transformation is a function of the form f of z equal to az plus b over cz plus d. So like I said, a fraction, okay, with the top linear and then the bottom linear as well, okay, where a, b, c, and d are all in c. So all these numbers you're seeing in this equation here, these are all complex numbers now. Now, if we have that AD minus BC is not equal to 0, then f is called a Mobius transformation. Now this right here might seem like a very curious condition. Why do we force that? Well, if we have this condition met, this function actually has a lot of special properties, and we're going to be seeing sort of one or two of them at the end of the video today. Now, for those of you that are really good with matrices, you should recognize this quantity. If we think about the matrix A, B, C, D, okay, then this quantity here, AD minus BC, is actually the determinant. So there is a little bit of linear algebra related to this for sure. Actually, there's a lot of linear algebra related to this, but we're not going to get too deep into that because this is not a linear algebra course. In any case, Mobius transformations, they're linear fractional transformations, so fractions with linear on top and bottom, with this extra condition that AD minus BC, so it's almost like a cross product thing, is non-zero. So we get a couple of immediate facts up in the upper right here. I'm just writing down what our function is so you don't forget. Firstly, if c is not equal to 0, then this function is holomorphic on c less negative d over c. Now we're actually going to be finding the derivative in a little bit, or actually I'll show you what the derivative is and I'll tell you how you can do it. But in any case, it should sort of make sense that is true, especially for c less minus d over c, because we can't even plug that value into here anyway without blowing up the universe. Okay. Now, if c is equal to 0, then our function basically becomes az plus b over d, which is a over dz plus b over d. So if c is equal to 0, basically we just have a linear function here. So, of course, that's going to be entire. But in any case, it is entire, meaning you know it's differentiable on all of c. And its domain is all of c, so we kind of actually get a really, really nice case there. And lastly here, if c is not equal to 0, so we're sort of back in this first case, then the quantity az plus b over cz plus d is never equal to a over c. So with the facts above, we get the following. Okay, so basically we get an invertible, meaning it has an inverse, bijection, 1-to-1 and onto. So let a, b, c, d be complex numbers with c not equal to 0, so we're not just dealing with a nice linear function. Then the function f from c, so less minus d over c, because we don't want to blow up, to c less a over c. We don't want a over c because, like we just said, that's not an output. So then the function from c less minus d over c to c less a over c, given by our linear fractional transformation, is a bijection. Okay, and it has an inverse function, f inverse of z equal to dz minus b over c minus cz plus a. Okay, now a couple of comments. We're actually going to prove 1-to-1 and onto in a second. You should be able to prove this inverse formula here just by using stuff you would do back in pre-calculus. So if you wanted to find an inverse, what do you usually do? You usually, switch x and y and solve for y again. That's kind of what you would do here in this case. So you guys should be able to do that, and we may do that in class, depending on how much time we have. But in any case, one thing I wanted to also point out, notice that f inverse of z actually has a similar form to f, right? So this is actually also going to be a Mobius transformation as well. So if f is Mobius, then f inverse is also Mobius. It's kind of like a really, really awesome thing. Okay, so proof of one-to-one. So let's suppose that f of z1 equals f of z2. Okay, so remember our goal for one-to-one proofs is we want to show that the inputs had to be the same thing. So if you get the same output, well, you had to plug in the same thing to begin with. Okay. All right. So if this is true, this means that just by the definition of our function, let me write PowerPoint, let me write. We get by the definition of our function, az1 plus b over cz1 plus c has to be equal to az2 plus b over cz2, that should be a d right there, cz2 plus d. Okay, and you might be like, great, now what do we do from here? Well, let's go ahead and cross multiply. So we're going to get az1 plus b times cz2 plus d is equal to az2 plus b times cz1 plus d. Okay, so that's after some cross multiplication. If we excuse me, if we FOIL both of these out, we're going to get az1 cz2 plus adz1 plus bcz2 plus bd is equal to az2 cz1 plus adz2 plus bcz1 plus bd. Whew. Okay, now this might look like a hot mess, but let's kind of parse it down a little bit. Notice we get some really nice cancellations. This bd will cancel out with this one. This az1 cz2 will cancel out with this az2 cz1. And all we're left with now is ADZ1 plus BCZ2 is equal to ADZ2 plus BCZ1. So let's move everything to one side. So we'll get, and factor, so if we move this over here, for instance, we're going to get AD times Z1 minus Z2 plus BC times Z2 minus Z1 is equal to 0. I'm sort of running out of room here. Let's go ahead and factor out a -1 from this quantity so we can factor out a Z1 minus Z2. And if you do that, you'll see that we get AD minus BC times Z1 minus Z2 equal to 0. A lot of algebra, so pause the video if you need to, but that's what we're going to get in the end. Okay, at least if we sort of go through it this way. Now, a couple of things. Remember, we're dealing with the Mobius transformation, right? So AD minus BC, we know that this is not equal to 0. Okay. Well, using the zero product property, then, we know that if two numbers multiply to 0, one of them had to be 0, right? Well, since we know this isn't 0, that means that this has to be 0. And if that's 0, well, what does that mean? Well, that means that Z1 equals Z2, which is what we wanted to show to begin with. So we know that this function is 1-to-1. All right, so for onto, remember we have to take something in the range, so let's let Z prime be in C less A over C. Remember, we're not mapping onto all of C. Remember, we don't get A over C as an output, so we're getting rid of that. So let Z prime be in C less A over C, and we want to show, for onto, that there exists a Z in C less minus D over C. Remember, we can't plug in minus D over C or we blow up the universe. We want to show there exists some Z in C less minus D over C such that f of Z, if I plug Z into the function, I actually get my output out. Okay. Now, by some algebraic voodoo, which I'm not going to show you, but you should be able to do, and it's actually related to finding the inverse of this function, let Z be dz prime minus b over a minus cz prime. Okay, so if you plug this z value into this function, okay, our Mobius transformation, then you'll actually get z prime out. So I'll let you guys do that as an exercise. Try this at home. Try plugging it in. Okay. Now, if you're curious how I actually got that, because that is I'm coming up with this out of thin air, it's just by doing some algebra. Okay, and it's algebra that's related to finding the inverse of this function. So it's something that you all are for sure capable of doing. In any case, our function is on 2, though. Okay, so some more facts about the Mobius transformation, or these linear fractional transformations. First of all, try showing it the inverse is as we said it was. Okay, and you should be able to do that. Think back to pre-calc. Okay, and let me be a little bit more specific with that. Think back to, well, how would you show that, or how would you find, let's say, the inverse of y equals 2x plus 1? Well, you would switch x and y, and you would solve for y. Okay, so if you do this process on our f of z equal to az plus b over cz plus d, you'll find the inverse is exactly what we said it is back in the proposition. Okay, so try that though. Make sure your algebra is still good. Using the quotient rule, okay, if you take the derivative of this function, okay, you'll see that you get AD minus BC over CZ plus D all squared. And again, that's just following straight from the quotient rule. Okay, and since we know that Mobius transformations have the property that AD minus BC is not 0, we also have that our derivative here is not 0, okay, because if the top's not 0, the whole thing can't be 0. And remember what that means from an earlier result back in, I think, chapter 2. I forget exactly what section chapter 2. But anyway, in chapter 2, remember we said if your derivative's not 0, then your function is conformal. And remember, conformal means that it preserves angles. Okay, so these Mobius transformations are actually really cool. Okay, they're bijections if you restrict your domain and range by 1 point. They have a nice derivative. Okay, it's not too bad. Just a constant on top divided by this thing squared. And they're also conformal. Okay, now we're actually moving to another really cool property in that Mobius transformations are kind of like Lego art. And by Lego, I mean like the Lego pieces. All right, so what do I mean by Lego art? I mean that Mobius transformations are really built out of other types of Mobius transformations. And this is kind of getting at the linear algebra idea too, if you guys remember a basis from linear algebra. But in any case, let's go ahead and introduce some special terminology and our Lego art characterization here. So we say that a Mobius transformation z plus b is a translation. Okay, and this is the same idea back from pre-calculus. If you took your input and you added some value, let's say 2, this would be a horizontal shift to the left 2 units. Now it's not quite the same in complex land because b is a complex number, so it's not just a shift left or right, but it's the same idea though. If we take our input and we add a constant to it, it's just basically some kind of move, a shift. Okay. A Mobius transformation of the form f of z equal to az is a dilation. Same idea back in pre-calculus. If I took 2x, or if I took x and then I multiplied it by 2, this would be a vertical stretch. Okay, so same idea in complex land. If I take our input and we multiply it by a complex number, we're just sort of affecting the magnitude. Okay, and then lastly, f of z equal to 1 over z is what we call an inversion. Okay, so which hopefully is pretty evident. It's 1 over z, right? So we're taking the reciprocal there. Okay, now what does this have to do with our discussion on Mobius transformations? Well, we get the following really cool result. Okay, so suppose f of z equal to az plus b over cz plus d is a linear fractional transformation. So maybe not a Mobius transformation, but a linear fractional transformation. Okay, if c is equal to 0, then like we saw earlier, our linear fractional transformation is really nice. It's just a linear function, right? A over dz plus b over d. Now, if c is not equal to 0, then we get something really cool happening. So then we can actually rewrite our function in the following way. Okay, now this kind of looks gross, but let me kind of break it down for you. So basically what we're doing is we're taking our input, we're translating it by d over c, and then we invert it, okay, then we dilate it by this crazy quantity BC minus AD over C squared, and then we translate it again, okay? So that's what this function is doing. It's basically how many transformations? That was 1, 2, 3, 4 transformations there. But the idea behind this, and it's kind of subtle, actually it's not subtle, it's staring you in the face. What this is telling us is that every linear transformation is basically built out of translations, dilations, and inversions. Okay? So if we think about these as sort of our Lego blocks, what this proposition is saying is that our linear fractional transformations and our Mobius transformations are built out of these 3 types of Lego blocks here. Okay? They build everything else. So that's why if you have a Mobius transformation in its general form, I called it earlier Lego art because this is really built out of these types of functions. Okay. Now this is going to come back, or we're going to see this again really, really soon in this video. This is going to help us prove something, or another really, really cool property of Mobius transformation. So don't forget this, even though it might be hard since we just talked about it. But okay. So what's that really, really cool property? It's the following. So Mobius transformations, okay, so if you have a linear fractional transformation with that property that AD minus BC is not equal to 0, okay, because that's what a Mobius transformation means, then that Mobius transformation actually maps circles and lines into circles and lines. And what I mean by that is, or what this theorem is saying, is that let's say we have a circle or we have a line, okay, in the complex plane. If you plug this, any point on the circle or on the line into a Mobius transformation, basically the function is just going to map it onto either another circle, so maybe it's a little bit bigger, and maybe it's over here now, or some kind of line. Maybe it's this line. Okay. And similarly, if you plug in any point that's on a line into a Mobius transformation, it's going to take it to similarly either a circle, maybe it's over here now, or another line. Okay. So Mobius transformations map circles to circles and circles and lines to circles and lines. Okay. Now it doesn't say which one it maps to. It all depends on your Mobius transformation. But in any case, this is kind of still a cool little result. Now let's kind of begin the proof a little bit, because this proof is a little, there's a lot of algebra in it, I'll say that. So just to begin this proof, note the first thing. So let's go ahead and let f of z be a Mobius transformation. Okay, now remember from our previous result, okay, that proposition, remember Mobius transformations are Lego arts, right? They're built out of these 3 types of Mobius transformations: dilations, translations, and inversions, okay? So if f is a translation, okay, meaning it's f of z equal to z plus b, then this theorem follows really, really nicely. It's clear. Then theorem obviously holds. Okay, because remember, what is a translation? Just think again, pre-calc terms. A translation just means that you're taking something and then you're moving it. So maybe it's up here now, okay? Or if you have a line, you're just moving it to a different place. Maybe it's like this now, okay? And that's what translations do. They're just going to take whatever you have and they're just going to move it by that beat, okay? So if your Mobius transformation is a translation, you're done, okay? Because again, translations, you're just moving. So if you have a circle, you're just moving it to another circle. If you have a line, you're just moving it to another line. Similarly, if f is a dilation, and remember dilation means that we're taking our input and we're scaling it by some complex number. Okay, so if we have f of z is equal to az, the theorem is also obvious because, well, what's a dilation do? Well, it would either take a circle and either make it into a bigger circle or a smaller circle, okay, which, cool, that's what the theorem is saying it's doing. And similarly for lines. Maybe it's doing something like this, or it's doing something like, I don't know, that. I don't know, in any case, you're just dilating a line, right? Okay, stretching it or shrinking it. Okay, so the only thing that we have to really worry about, though, to prove our theorem is inversions. What happens in an inversion? And that's not clear. It's not like you can take 1 over the circle and then boom, it's still a circle. So the only part that's missing in this theorem that we need to prove is what happens if you have an inversion. Because once we have all those, since Mobius transformations are made out of these 3 Lego blocks, then we know that obviously we have that this theorem is true. Okay, so the only thing that's left is, what about inversions? Okay, that's the non-obvious part. Okay, so how do we prove it for inversions? Well, we have some algebra to do, everyone. All right, so first step, and again, prepare yourself for algebra. So let's suppose that we have a circle. Now, just like in real land or calculus, circles are given by the following equation. X is equal to r squared, so our radius squared, is equal to x minus x naught squared plus y minus y naught squared. Okay. Now, if we're given a circle, we can always transform, and this is going to sound really funny and like, why would you ever want to do this? But given a circle, we can always transform it into this equation here. Alpha times x squared plus y squared plus beta x plus gamma y plus d is equal to 0, where beta squared plus gamma squared is greater than 4 alpha delta. Okay. Now, you might be like, why would we ever want to do that? Well, it actually turns out that this equation here is going to be more useful when we start to prove that inversions do take circles to circles or lines and lines to circles or lines. Okay, so this equation actually is going to be, even though it looks sort of more gross, it's going to be more useful for us. Okay. Another positive about this equation is that it sort of encompasses both circles and lines in it. If alpha is equal to 0, notice that this is basically a linear equation, right? Linear in x and y. Okay. And if alpha is not 0, then, well, again, this is our circle. So it's sort of an equation, even though it's more complicated, it actually encompasses sort of 2 things that our theorem is talking about, lines and circles. Now, how do we actually show that we can do this? Well, we're going to kind of start backwards, okay? Kind of like our epsilon delta proofs in a way, okay? So what I'm going to do is, let's suppose that we have an equation of this form, okay? I'm going to show you that we can get the equation of a circle if we have this condition right here, okay? And then if you follow my algebra backwards, you can sort of start here and then end here as well. Okay, and I'll explain that in a little bit. But in any case, let's go ahead and start backwards. Let's suppose that we have this crazy equation. I'm going to show you that we can actually get the equation of a circle provided beta squared plus gamma squared is greater than 4 alpha delta. All right, so let's suppose this. Are we all supposing? Okay, so the first thing we're going to do, let's go ahead and distribute alpha. So we're going to get alpha x squared plus alpha y squared plus beta x plus gamma y plus delta is equal to 0. Okay, now what we're going to do, and this is why I call this algebra for the win, we're basically going to complete the square on x and y. Okay, so remember, you're completing the square back from high school or middle school, depending on where you took it, but I know you've all have seen that before. We're going to complete the square. Okay. So I'm going to group together my x terms and my y terms. So we're going to get alpha x squared plus beta x plus alpha y squared plus gamma y plus delta equals 0. Okay. Now I'm going to complete the square on x, and then I recommend you do this by pausing the video and trying it yourself. But let me show you the broad strokes of completing the square if you've forgotten it. So whenever you're completing the square, your first step should be make the number in front of your x squared term a 1. Okay, so what I mean by that is, we're going to factor out alpha. Okay, so that's the first step of completing the square. Now our second step, this seems like math magic, and it sort of is, but what we're going to do is we're going to take the b term, the new b term, so beta over alpha, okay. We're going to divide it by 2, and square it. Okay, so we take our b term, divide it by 2, so I put a little 2 in our bottom piece, and then we square it. Okay, now why are we doing this? Well, if I take my equation here, alpha x squared plus beta over alpha x, and if I add and subtract this quantity, completing the square says we get something nice. Okay, so I'm going to add and subtract our quantity here. By the way, I did simplify it a little bit, so make sure you're okay with that. Oops. Okay. Now again, you might be like, why the heck would you ever do this? Well, again, completing the square tells us that these first 3 terms factor into something really nicely. In fact, they factor into the following. Okay, it'll be x plus whatever term we had here before squaring, beta over 2 alpha squared. Okay, so those first 3 terms actually become a perfect square if you do this add and subtract trick. Okay. By the way, I know that looks like a 2 prime there. Let me get rid of that. Boom. Okay. Now we're not quite done yet because we still have this minus beta squared over 4 alpha squared, right? So we still have that floating around. Okay, so what we're going to do, let's go ahead and redistribute alpha so that we finally get alpha x plus beta over 2 alpha squared minus, now one of these alphas will cancel out, we'll get beta squared minus 4 alpha. Okay, so there's a crash course in completing the square, although you probably haven't seen completing the square in this generality, but in any case, it's definitely not something that's above you all for sure. Okay, so if we do that to both these terms here, if we complete the square on x and y, we'll get the following. So we'll get alpha x plus beta over 2 alpha squared minus beta squared over 4 alpha. Okay, plus, now if you want to practice this, I recommend pause the video, try to complete the square on y here, and then compare with what I get. Okay, so go ahead and pause if you want to. But what you should get is alpha times y plus gamma over 2 alpha squared minus gamma squared over 4 alpha plus delta. Okay, so we've completed the square on x and y, and next what we're going to do, and notice you should be like, hey, this is actually really good, because remember, what are we trying to do? We're trying to make it into a circle equation, right? So now we have our squares here going on. Okay, the only thing is we don't have that r squared, right? So our next step is, well, let's go ahead and move all these constants to the right hand side, and then we're also going to divide by alpha as well. But in any case, let's go ahead and do that. So we have alpha x plus beta over 2 alpha squared plus alpha y plus gamma over 2 alpha squared. Okay, and then I'm moving everything to the right hand side, so we have, and I actually already forgot what we're moving over to the right. Let's see, we'll have beta squared over 4 alpha. So we'll have beta squared over 4 alpha plus gamma squared over 4 alpha minus delta. Now let's divide both sides by alpha. What do we get? We get x plus beta over 2 alpha squared plus, oops, y plus gamma over 2 alpha squared is equal to, now we're dividing both sides by alpha, so we're going to get beta squared over 4 alpha squared plus gamma squared over 4 alpha squared minus delta over gamma. I'm sorry, alpha. Okay. Now, the left-hand side is great. Remember, we're trying to get the equation of a circle, right? That's exactly what we want. Now, the right-hand side, remember, we want something that's like an r squared, right? So let's sort of combine all these things and make sure we get it into one number. Okay, so if I go ahead and add these fractions together, you'll see that we get beta squared plus gamma squared minus, let's see, it'll be 4 delta alpha all over 4 alpha squared. Okay. Now I'm not going to write it as something squared because that would be sort of a pain in the butt. But, well, actually it would look really, really bad. But the thing I want to to make you guys see, or hopefully it's clear to you all, remember this is supposed to, if this is a circle, okay, this is supposed to be a number that's greater than 0, right? Our radius should be greater than 0 because it's a radius, right? It's a distance. Now, the only way that this thing would be greater than 0, how do we make this greater than 0? We would have to have that the top here is greater than 0, because 4 alpha squared, remember alpha is not 0, right? So 4 alpha squared, that's positive. So the only thing that could make this negative is the top. Okay, so if we want to make sure that this is positive, we're going to require that beta squared plus gamma squared minus 4 delta alpha is greater than 0. And if we simplify this inequality a little bit, we'll get beta squared plus gamma squared is greater than 4 delta alpha. Okay. Now you might be like, what's the point of that? Well, remember, this inequality, let me go back a slide, that's exactly what we wanted right here. Okay, so that's why if we have this algebraic equation here that looks really, really messy with this condition, beta squared plus gamma squared is greater than 4 delta, then we can convert it into an equation for a circle. Okay, so that's where that funny inequality comes from there. Okay, so now again, what I recommend for you guys to do is complete the square, try completing the square. And the second thing I want to say is, notice we have our equation now. We have this is equal to this, right? Which is sort of our radius squared. Now, if you work it backwards, okay, you can actually get the equation, the crazy equation as well. Okay, so what do we have at this point? Well, we now have that if we have a circle, we can convert it into this equation. And if you use my calculation here, this long crazy algebra, and you work it backwards, you can actually go the other way. If you're starting with a circle, you can actually get this equation, and then vice versa. Okay, so how does that help us with the proof, though? All right. So the proof of the theorem, so remember, Mobius transformations are composed of translations, dilations, and inversions. Like we discussed earlier, translations, good, because it's just a shift. Dilations are good, because it's just a stretch or a compression. And now inversions were the things that we had a little bit more difficulty with. Okay, so the only thing we need to show to prove this theorem, because again, translations and dilations are good, we need to show that this is true for inversions. Okay, I'm going to put a little question mark there. Is it true that if you have an inversion, that an inversion will map circles onto circles and lines, or lines onto circles and lines? Okay, so that's the last part of the proof, or the theorem, the part of the theorem that we need to prove. If we can prove that, we're good, because any Mobius transformation is some kind of composition of these things, and if it's true for our Lego blocks, it has to be true for our Lego art. Okay, so let's go ahead and think about f of z as an inversion. Okay, and let's go ahead and write z equal to x plus iy. Now further assume that z is on either a circle or a line, because remember, what are we trying to show? We're trying to show that this function maps circles onto lines and circles, or lines onto circles and lines. Okay, so we need to assume that z is on a circle or a line. So basically what we need to show is that our transformed, if I plug our z into our Mobius transformation, we're going to write it as, well, it's 1 plus x over x plus iy, but we can write that as u plus iv, satisfies our transformed equation. Okay, because if we can show that this quantity here satisfies our transformed equation, that crazy looking thing that we have here, then we know that this is true for inversions as well. Okay, so how do we do that? Well, we have to do a lot more algebra. Okay, so again, our goal, just to state it again so that we're all on the same page, we plugged z into our function to get this. Okay, so we're going to write 1 over x plus iy in terms of its real and imaginary parts, u plus iv, like we've done in the past. Okay, and we want to show that u plus iv satisfies our crazy transform equation, because then we know that it's either a circle, or it's on a circle, or it's on a line. Okay, so our goal, show u and v satisfy our transformed equation. Okay, so how are we going to do that? Again, we're going to do lots of algebra. Okay. All right, so the first thing we're going to do to show this is we're going to sort of take our equation here and we're going to adjust it a little bit. So u plus iv, okay, which we're saying is 1 plus x plus iy, what we're going to do to it is we're going to multiply by the conjugate. A trick we have definitely seen at some point, either in class or in a video. Okay, now why am I doing this? Well, what are we going to get on the right-hand side? We're going to get, so if we actually multiply everything throughout, we'll get x over x squared plus y squared plus I minus y over x squared plus y squared. Okay, so I recommend do the algebra on your own, but if you do the algebra on your own, you should see that you get this. Now what this tells us is that u, our real part, has to be x over x squared plus y squared, and v has to be the imaginary part, minus y over x squared plus y squared. Okay, now remember, x and y, since we're assuming that z, our input, was on a circle or a line, remember x and y satisfy our transformed equation, right? Okay, so we know that by our transformed equation, we know that this is true. Okay, because again, remember x and y, they're coming from a point that's lying on a circle or a line. So we have our crazy equation going on. Okay, well, if we do some algebra, okay, let's divide both sides by x squared plus y squared. So we'll get alpha plus beta x over x squared plus y squared. And then what we're going to do here, we're going to be a little bit tricky. We're going to say, we're going to write gamma y as minus gamma minus y over x squared plus y squared plus delta equals 0. Okay. Now you might be like, why did I do, and I know that looks funky, let me fix that really quick. Why did I do that? Well, I'm going to eventually substitute u's and v's in. Okay. So we divided both sides by x squared plus y squared. Okay. Whoops. And I'm missing here as well. There we go. And so we get this equation right here. Okay. Well, again, like I just sort of spoiled, what is this quantity right here? This is u. And what's this quantity right here? That's v. Okay. Now, if you think about it, what is 1 over x squared plus y squared? That's just u squared plus v squared. So this is alpha plus beta u minus gamma v plus, so again here I'm using the fact that 1 over x squared plus y squared is actually equal to u squared plus v squared. Okay. Delta u squared plus v squared. Boom. And now we're happy. So notice that u and v, okay, so this equation that we ended up with is exactly an equation of the form that we had up here. So delta and alpha sort of changed places a little bit. Beta and gamma are roughly the same thing, although we have to adjust gamma with this minus sign here. But in any case, notice it's essentially the same equation here that we have. And what does that mean for us? That means that u and v, okay, are sitting on either a line or a circle. And that's exactly what we wanted to show. Remember, u and v came from our inversion, right? So what this means is that inversions also map circles and lines, it's not how you spell circles, to circles and lines. Boom. So we have this really, really cool result. If you have a Mobius transformation, Mobius transformations take circles